Now some more formulas. These are the power reducing formulas because they enable you to start with the square of one of these trigonometric functions, sine squared, cosine squared, tangent squared, and turn it into an equivalent expression that only involves a trigonometric function to the first power. By the way, this comes in handy in certain calculus contexts when you're doing integration or anti-differentiation of certain functions that involve sine squared or cosine squared. So whether or not you ever do that, that's something I'm familiar with that these are used for. And then sort of related to these, because if you start with sine squared of u equals something and replace u with u over 2, which means over here you've got 2 times u over 2 or just u, and take square roots, this turns into this half angle formula about what the sine of u over 2, half of u, is equal to. And it's got a plus or minus because if sine squared equals an expression, the sine would equal the positive or negative square root of that thing. Now, which one it actually turns out to be depends on whether the angle u over 2 is in one of the quadrants where sine is positive or one of the quadrants where sine is negative. So these half angle formulas let you take the sine of half an angle, or the cosine or the tangent of half an angle, and relate it to something involving just the angle that that's half of. So some examples using these formulas. One example is now we have another way of finding an exact value for something like the cosine of 15 degrees. One way to find that, like we looked at last time, was that 15 degrees is equal to 45 degrees minus 30 degrees, both of which we know exact values for. But another way we can deal with this is by thinking of 15 degrees as 30 degrees over 2, and we do know about 30 degrees and its cosine. So according to this half angle formula, with the part of u being played by 30 degrees, the cosine of 30 degrees over 2 would equal plus or minus the square root of 1 plus the cosine of 30 degrees over 2. Now we know exactly what the cosine of 30 degrees is. At least I know what it is. If you don't remember, you can check it on the unit circle. It's the square root of 3 over 2. And then we've got plus or minus the square root of 1 plus the square root of 3 over 2 all over 2. I can simplify that complex fraction by multiplying everything on the numerator and everything on the denominator by 2. That gives us a 2 plus square root of 3 over 2 times 2 is just the square root of 3 over 4. And then we have the square root of the numerator, square root of 2 plus the square root of 3, over the square root of the denominator, square root of 4 is 2. And I'm going to dispense with the plus or minus because I know that 15 degrees is an angle in quadrant 1, and its cosine is a positive number. So the cosine of 50 degrees is exactly the square root of 2 plus the square root of 3 over 2. Let's use these expressions, these half angle formulas, to simplify the square root of 1 plus the cosine of 10x over 2. So look at these formulas and see if you can see something that has the same pattern as the square root of 1 plus cosine of 10x over 2. I see two different formulas that involve the square root of something, but one of those formulas has a minus and one has a plus. So we want to look at the one with a plus. And the part of u in the formula in this specific example is being played by 10x. So the formula tells us that this is equal to the cosine of u over 2, where the part of u is being played by 10x. So u over 2 would be 10x over 2, or just 5x. And so this is equal to the cosine of 5x. Let's simplify the square root of 1 minus cosine pi over 2. Now that fits this first pattern with the minus. That's the square root of 1 minus cosine u over 2, where in place of u, we just have a pi. So that would be equal to the sine of pi over 2. And I know what the sine of pi over 2 is. It's 1. Now, if I had not used the formula, but just directly said, oh, the cosine of pi is -1, then this would have been the square root of 1 minus -1 over 2, which would be the square root of 2 over 2, which would be the square root of 1, which would be 1. Now, even more formulas, product to sum formulas and sum to product formulas. Product to sum formulas start with a product, two sines and or cosines multiplied together, and turn them into something involving plussing and minusing. And then the sum to product formulas start with a sum or a difference of sines or cosines and turn it into a product with cosines and sines multiplied together. So let's see these formulas in action. Let's say we start with the cosine of 5 theta times the cosine of 9 theta. Which of these patterns does that fit? Well, we've got cosines. These are both cosines of two different things multiplied together. So that's like cosine u times cosine v, where in place of u we have 5 theta, and in place of v we have 9 theta. So according to that formula, that would be equal to, okay, I'm just going to write this all out, but in place of u, I'm going to write 5 theta, and in place of v, I'm going to write 9 theta. So it's equal to 1/2 times, inside brackets, the cosine of 5 theta minus 9 theta, plus the cosine of 5 theta plus 9 theta. And of course, 5 theta minus 9 theta would be -4 theta. 5 theta plus 9 theta would be 14 theta. So I can write this as 1/2 times the cosine of -4 theta plus cosine of 14 theta. Now that is equivalent to 1/2 times the cosine of +4 theta plus cosine of 14 theta. One way you can see that is that cosine is an even function, which means that the cosine of negative something is the exact same thing as the cosine of positive that thing. But also, we could have just switched the order at the very beginning. These are just two things multiplied together, so I can put the second thing first and think of it as cosine of 9 theta times cosine of 5 theta. And then here we would have had 9 theta minus 5 theta, which was 4 theta. Okay, how about this? Sine of 7 theta minus the sine of 3 theta. Which pattern does that fall into? Okay, we've got sines, and we've got a minus in the middle. It's like the sine of u minus the sine of v, but in place of u we have 7 theta, and in place of v we have 3 theta. So I'm going to write what that's equal to. I'm going to copy this expression here, except where there's u, I'm going to put 7 theta, and everywhere there's a v, I'm going to put 3 theta. So it's 2 times the cosine of 7 theta plus 3 theta over 2 times the sine of 7 theta minus 3 theta over 2. And then I can clean that up a little bit. 7 theta plus 3 theta would be 10 theta, divided by 2 would be 5 theta. 7 theta minus 3 theta would be 4 theta, divided by 2 would be 2 theta. So this is equal to 2 times the cosine of 5 theta times the sine of 2 theta. And here's one with some actual angles, some actual numbers. Sine of 75 degrees minus the sine of 15 degrees. Same formula, this time in place of u we have 75 degrees, and in place of v we have 15 degrees, so I just copy over what that's equal to, but with 75 degrees and 15 degrees in place of the u and the v. 75 plus 15 would be 90, divided by 2 would be 45. 75 minus 15 would be 60, divided by 2 would be 30. And then I happen to know that the cosine of 45 degrees is exactly square root of 2 over 2. And the sine of 30 degrees is exactly 1/2. And so we're looking at 2 times the square root of 2 over 2 times 1 over 2, which simplifies down to the square root of 2 over 2. You could check that on a calculator if you want. Make sure it's in degrees mode. Ask it what the sine of 75 minus the sine of 15 degrees is. And then compare that number with the square root of 2 divided by 2. It should be the same thing, 0.707 something.